Hello, everybody. Welcome to week 3 of environmental concerns. Today, we're going to be learning about the ozone layer and the Montreal Protocol. And it's me, Michael Leclerc, your teacher. Before we get started with the presentation, there's a couple quick things. First off, there's going to be another worksheet for this week. Important to note that it's not worth any marks or anything of that sort. It's strictly to be used as a study tool and something that can help further your own education with the topic. Just gives you some ideas of some of the questions I may be asking come midterm and final. I've also made a quick little fun Jeopardy for this week's topic. There will be a link for that in week 3 of the the weekly learning section. You can find it in that week 3 folder, and you can have it take a look through that as well and play along with it if you want. So that being said, without further ado, let's get into the actual material for this week. So first off, we have our atmosphere. You guys are probably all familiar with it. If you're not, well, it's what we breathe every single day of our lives. The Earth's atmosphere is made up of several layers that surround the planet. We're going to be getting to those in a second. The atmosphere itself is made up of a lot of different chemicals and gases, but the predominantly common ones are nitrogen, which makes up about 78%, oxygen, which is 21%, and then the other surrounding gases like hydrogen, making up only 1% of that atmosphere. The atmosphere itself continues way up into space, and there's no actual hard limit on the atmosphere, if you will. It just kind of gradually fades away into the nothingness of space. So the atmosphere itself is divided up into 5 different layers, as you can see from this picture just above my head here. We've got the troposphere, which is our first layer, the closest one to us. Then we have the stratosphere, the mesosphere, the thermosphere, and then finally the exosphere up at the very top. So you might have to zoom in a little bit for this one if you really wanted to take a look at it. This is kind of trying to illustrate visually how big each layer is in relation to each other. So the troposphere that we live in, that's right up against the surface of the Earth, is that tiny little red part. Oh, there, you can't even see my finger's going to go off the screen or not through the webcam. But basically, I'll use my mouse, I guess. It's probably a better way. This little red part right at the bottom there, that's our troposphere. Very small little section, but obviously very important. Up next is our stratosphere, the yellow section, the mesosphere, which is the green, and then we got the thermosphere, which takes up quite a large section before the exosphere itself. So, in a nutshell, this is our atmosphere. Looking just in terms of the temperature, it's interesting to note that as we go up in the atmosphere, especially the troposphere, our temperature decreases, as you would imagine. But once we start getting to the stratosphere, the temperature actually starts increasing again, which is probably not what you would expect. Once we get into the mesosphere, it drops back down again. And actually, when you get into the thermosphere, the temperature actually skyrockets. A large reason for this is because the sun, if you think about it, the sun is obviously something that heats our planet up. It also heats the environment, the atmosphere up, right? The problem is that the stratosphere is, as we'll get into in a little bit, where the ozone layer is located, and more importantly, that's where the UV rays from the sun actually excite the atoms, the actual atmospheric gases there, and allow the temperature to increase. The mesosphere, as you get higher up into the mesosphere and beyond, there's less gas. It starts dissipating more, right? Gas just likes to fill its space, right? And well, if you have space itself, there's only so much you can do with it. Thermosphere is actually hotter because in theory, it's hotter. It's probably the wrong word to use for it. But the way that it works is the sun is basically completely hitting the atoms up in the thermosphere, the gases up in the atmosphere, without any protection, right? But the problem is that there's so little gas that there's no way for the excitable energy from these gas molecules. They once something gets energy, it gets heated, it moves quicker, right? It's the same idea when you add heat to water. It boils, it turns into steam. So the thermosphere gases, they also get more excited from the energy they gain from the sun. However, even in their excited state, bouncing around like crazy in the thermosphere, there's so few gas molecules up there, they don't really have anything to interact with. So you actually wouldn't even really notice any heat. It would actually show a very cold temperature if you were to use a thermometer, only because those very hot molecules aren't able to transfer their heat anywhere, and so it's not actually like registered, if you will. So first off, we got the troposphere. So it's the lowest layer. It's where all of or most of our clouds are found, and basically almost all of our weather occurs here. It's the one that you guys are obviously the most familiar with because this is where we live. As you can also imagine, this is where most of the atmospheric mass is located. Since I was saying that as you go further up into the atmosphere, you start getting less and less gas present. It's just like less concentrated, if you will. Most of the concentration is down at the bottom. And so that's where most of the mass of the atmosphere is actually located. Next up is the stratosphere. This is the layer that you typically would have your jets flying around in, and this is also where the ozone layer is found. So we'll be talking about this a little more in just a little bit. Next up, we have the mesosphere, or mesosphere, depending on how you want to say it. Sometimes it's referred to as the near space layer, or just near space in general. They have a high concentration of iron and other metal atoms, and this is actually due to, this is the layer that kind of protects us, funny enough, from meteors that would try and strike us. So they burn up in the atmosphere in this layer. And that iron and other metal atoms from the meteors actually remain in this layer. So here's the thermosphere again, extremely hot, as high as 2,500 degrees Celsius or more, and this is kind of what I was indicating. But it's practically a vacuum in the thermosphere. The low density of gases is actually insufficient, as I was saying, for those molecules to actually conduct that heat. So the molecules themselves will be superheated from the solar radiation, but they won't be able to conduct it or anything. So but despite this, an object or observer in the thermosphere would actually experience cold temperatures. The International Space Station and the Tiangong Space Station are also found up here. So it's essentially space at this point, but there is still some of that gas from Earth's atmosphere, so it's considered part of our atmosphere. As I said, once we start getting into these layers, especially the thermosphere and the exosphere, the next and the last one, it starts getting a little fuzzy on what's considered space and what's considered our atmosphere. And I mean, the picture itself says 1,000 words for it, right? We're talking about the exosphere, and you got a satellite here. Since the exosphere actually gradually fades into outer space, there's no clear upper boundary of this layer. Some scientists actually don't even believe that this layer actually exists at all, and that the thermosphere is considered the last layer, because after that it's just outer space. If you do believe the exosphere is a layer, however, one believed uppermost edge of the exosphere is 190,000 kilometers, which is about halfway to the moon. This is based on a faint glow of ultraviolet radiation scattered by hydrogen atoms found at heights of about 100,000 plus kilometers above the Earth's surface. But because there's still little bits of air there, presumably from Earth, it's considered a layer. So to kind of recap quickly on our atmosphere, we got the 5 layers, right? We got the troposphere, which is where most of our weather and clouds are found. Got the stratosphere, where jet aircrafts fly and the ozone layer is found. Meteors or rock fragments burn up in the mesosphere. You have the thermosphere, which is a layer with the auroras are found. It's also where the space shuttles orbit. And then finally you have the exosphere, which is the upper limit of our atmosphere. So the layers of atmosphere we are concerned with today involving the ozone layer are the stratosphere and the troposphere, as you can see here. The ozone layer is actually located in the stratosphere right at the very bottom of it. It's a spot called the tropopause, which is basically the border between the two. So the ozone layer. Once we understand how ozone is made and its purpose, we can then understand it's important to us on Earth and why we need to protect it. So I'm kind of blocking this a little bit, so I'll throw my my ugly mug off for a second. But you can see there that O2 plus O2, or O plus O2, oxygen. So an oxygen atom with an oxygen molecule create O3, which is your ozone. Oh, okay. So ozone layer serves 2 main purposes. First off, it absorbs some of the higher energy UV rays from the sun, the same way a cloud will absorb and reflect some of the visible light. The parts of the UV light absorbed or reflected is very harsh on the eyes and the skin of humans, other animals, and can cause very bad sunburns, among other things. It's also been linked, as I'm going to show here, the formation of cataracts in the lens of the eye, which makes you nearly blind without modern medical treatment. Secondly, the ozone layer acts as a greenhouse gas. So, man-made chemicals damage the ozone layer over the South Pole. This is going to really skip ahead for us a little bit here. We're going to come back to this, but basically they took temperatures in the South Pole, and they noticed a large change in the amount of ozone that was being present above Antarctica. Over most of the Earth's surface, the sunlight causes new ozone to form high in the stratosphere, and at the same rate, chemicals in the air break it down to normal oxygen molecules. And then these oxygen molecules again go on to make ozone, and then back and forth. This is something called the oxygen cycle. However, back in the Arctic and the Antarctic circles, as you guys know, the sun sets for up to 6 months out of the year, so there's no sunlight, meaning that since there's no sunlight, you don't have those UV rays producing or helping to produce ozone molecules. Without that, obviously ozone is kind of what you have is what you have, right? You got to wait the 6 months or however long until the sun comes back and you can start producing new molecules. So the stratospheric ozone layer absorbs UV emitted by the sun. If all of the solar UV light were able to penetrate the stratosphere and troposphere and reach the Earth's surface, it would seriously damage our ecosystem. For example, ultraviolet light kills microbes, bacteria, and fungi. These microscopic forms of life play a key role in plants being able to process and absorb nutrients from the soil. And then we can have that cascade effect that I was talking about last week, where if plants start dying off, then the animals that eat those plants would start dying off or just, migrate somewhere else, which would in turn affect their predators and so on and so on and so on. So we got a quick video here that we're going to go over. I actually get my face off of here so that you can focus on the video and not me just standing there staring at the screen awkwardly for a couple minutes.
In this video, we will learn about the two main layers of our atmosphere. The troposphere, full of weather and bad ozone, and above that the stratosphere, where good ozone protects us against dangerous ultraviolet light. Our atmosphere is made up of gases, mostly nitrogen and oxygen. They are held to the Earth by gravity, a sort of ocean of air. Because air is compressible, it gets less and less dense as you get further from the Earth. Let's consider the first 50 kilometers where 99% of the atmosphere is found. Visible sunlight passes through the atmosphere and warms the ground, heating up the air at ground level. As the colder air above sinks, it pushes up the warmed air, which is less dense due to expansion. This movement, known as convection current, gives us our weather systems. The atmosphere gets colder and colder till you reach about 10 kilometers, the tropopause, where the temperature is coldest. Below this is the troposphere, containing 80% of our air, and all the weather. Above the tropopause we have the stratosphere. This is a layer of thin air which is hot on top because it's heated from above by ultraviolet radiation absorbed by the good ozone and cold underneath, making it dynamically stable. Contrast this with the turbulent troposphere. If you have ever flown in a jet aeroplane, you may have had a bumpy ride after takeoff through the turbulent troposphere, but once you're above the clouds, above the weather, your journey is smooth. Propeller planes cannot fly this high because the air is too thin for the propeller to grip the air. So where does this good stratospheric ozone come from? Pause the video and think of the formula of ozone. Well, ozone is an allotrope of oxygen. Its molecules are made of 3 oxygen atoms bonded weakly together. It is an unstable gas which slowly decomposes back to molecular oxygen. The ozone in the stratosphere is continually being made and broken by the ultraviolet light in the ozone-oxygen cycle. To start with, UV gets absorbed in the stratosphere by molecular oxygen, which splits into 2 fast-moving atoms. These fast-moving oxygen atoms collide with air molecules around them, nitrogen and oxygen. This slows the free oxygen atoms down, enabling them to bond weakly with the molecular oxygen to form ozone. If they're moving too fast, they simply bounce off. The energy they shared with the molecules in the air heats up the upper atmosphere. The oxygen atom has now joined with an oxygen molecule to form ozone. Ozone is very effective at absorbing ultraviolet light, which causes the ozone to split back into an oxygen atom and an oxygen molecule again, keeping the upper atmosphere warm. Ozone reforms as before once the oxygen atom is moving slowly again. The ozone is spread out through the stratosphere, shown here in black. Why do you think there is so little ozone high up and low down? Remember, we need ultraviolet radiation and oxygen to make ozone. Pause and think. Well, here there is too little oxygen, and here, near the tropopause, the point of lowest temperature where the troposphere and the stratosphere join, there is no ultraviolet light available. It has all been absorbed by the ozone further out. So this is the ozone layer. If the ozone were squashed together like a solid, it would only be the thickness of a sheet of cardboard, but it is actually a gas spread out over 20 or 30 kilometers. Before our atmosphere was filled with oxygen, the UV reached the Earth's surface and prevented life from emerging onto the land. Ozone is also present in the troposphere, formed mainly by the action of sunlight on pollution from motor vehicles. Here, it helps to form photochemical smog and is a pollutant.
Okay, so that was very educational. We got a couple other videos that will be thrown in over the course of this lecture here. So it's also estimated that about half of the atmospheric oxygen that's been used for us to breathe and to actually create this ozone layer is actually generated by phytoplankton that live in the ocean's surface. Green algae is a form of phytoplankton. You've probably seen it. A significant increase in UV light would also diminish the phytoplankton population. So it'd be kind of a rolling effect here where if we were to lose part of our ozone layer, or the ozone layer just became not as effective and started having more UV rays escaping, or I guess getting down to the Earth's surface and killing off the phytoplankton wouldn't be making as much oxygen anymore, which would in turn mean less of an ozone layer being created. So additionally, an increase in the amount of ultraviolet light would also dramatically increase the incidence of sunburn in humans, as well as causing stress and potentially death of many types of plants and animals. There's generally 3 different types of UV rays that account for come from the sun. You can see them from the image here. We have UVA-A, UVB, and UVC. So UVA accounts for 95% of the UV radiation that reaches the surface. It can penetrate into deeper layers of skin and is responsible for that immediate tanning effect that you see. Although UVA and UVB are both dangerous, UVA is more of a threat just due to a larger amount reaching the Earth's surface. It's just due to overwhelming amount of it compared to UVB. And to be blunt about it, it's present all day, every day, even when it's cloudy. If you see daylight, aka you look outside and it's day, UVA rays are there. They're considered sun's silent killers because you just don't see their effect generally. They penetrate deeper into the skin and steadily destroy key substances in the skin that give firmness and elasticity. As a result, it's easy to figure why they're the leading cause of wrinkles, and they're a major contributor to most skin cancers. UVB rays, on the other hand, are the ones that you're always warned about by your parents and by other, commercials and other, public service announcements and stuff like that. They're the ones that cause those painful and visible sunburns that you see. They can also cause skin cancer. These skin cancers usually originate in the epidermis, which is your top layer of your skin, since they can't penetrate as deeply as UVA. They are often referred to as the burning rays. There is one positive benefit to UVB rays radiation. It helps the skin produce vitamin D. This is kind of an example of the saying, the dose makes the poison. A small amount can be beneficial for producing necessary vitamins for bone and muscle health. However, too much causes the previously mentioned problems. This amount will vary from person to person, and it's based on a ton of variables, such as your diet, your skin color, your sunscreen usage, worn clothing, where you live, time of day and year, etc., etc., etc. And then finally, you have the UVC rays, which are very, very dangerous, but thankfully the ozone layer prevents them from reaching the surface. If you were exposed to UVC rays, say like you jumped into space somehow, or the ozone layer just disappeared overnight, it could cause severe burns to your skin and eye injuries as well. Thankfully, these burns or eye injuries can resolve themselves and they heal with no known long-term damage. And this is because UVC rays have the lowest penetration depth of the three. Do you notice a bit of a trend there where as you go along the alphabet here, UVA, UVB, and UVC, your actual penetration ability kind of lessens. Since the penetration depth, oh, sorry, there's a cat tail here. Come on, Rufus. Since the penetration depth is very low, skin cancer, cataracts, or permanent vision loss is also thought to be pretty low as a risk from UVC. Sometimes exposure to UVC rays can cause vision loss, though, for a couple of days. These injuries can occur with very, very short exposure to UVC rays, as short as seconds or minutes. So you can imagine if UVC rays were a permanent issue to be dealt with outside, we'd never survive. Or if we did, it'd be a very different life than we live now. So to recap with that, exposure to UV light also causes cataracts and is currently the leading source of blindness in people over 40. Conceivably, increases in ultraviolet light would start to induce blindness at a younger age, could even cause blindness in animals that have not adapted to an increased level of UV light. And if you are unfamiliar with cataracts, it's essentially, as it says in this image, I'll take my my face off here again for a second. It's the clouding of the lens in the eye that affects vision. So the lens kind of gets clouded over, and that's the cause of the cataract. So studies have now linked ultraviolet light increasing the risk of cataracts in younger people. The ozone layer does play an important role in making the Earth habitable by absorbing most of the solar ultraviolet light before it reaches the Earth's surface. So as you can see in this image here, the UV rays get stopped for the most part by the ozone layer, and this big arrow is more than likely the UVA rays that we were talking about making their way down to the surface. So ozone is an inorganic molecule. The chemical formula is O3. It's a pale blue gas with a distinctively pungent smell, simply made by diffusing dioxygen by UV light, as shown in that earlier shown movie. Electronic air cleaners are capable of creating ozone because they rely on electrically charged particles, which is ionizing, to make the dust particles attracted to the metal plate inside the appliance, so they can create this unique odor in the house. Ozone is a known lung irritant and asthma trigger. While many units produce negligible levels of ozone, there are some brands and models on the market that exceed government safety standards still to this day. And this kind of also, this last point about them being a known lung irritant and asthma trigger is part of the reason why you see smog forming in city centers. People living in cities, especially when you see smog alerts going on, it can be asthma triggering and just an irritant to your lungs in general. To add to that, in general, ozone is minimal and most of the time unnoticed on the Earth's surface in the troposphere, but it's very much present in the upper part of the stratosphere layer of the atmosphere, making our ozone layer. Because of ozone's molecular characteristics, it shields us from harmful UV rays from the sun, the rays that can burn our skins, cause cancer, fade colors on furniture and other items, which admittedly is probably less of a problem than, skin cancer, turn leaves to yellow, which is bleaching, and eventually kill many organisms living on the Earth's surface and inner waters. So ozone gas doesn't just coat our Earth's stratosphere. It can be found on the Earth's surface as well. It is used for such things as bleaching, for sterilizing water, and removing unpleasant smells from products. It's referred to as an allotrope. So the term allotrope refers, I'll take my face off again here because there's this image here. The term allotrope refers to one or more forms of a chemical element that occur in the same physical state or a gas in the case of ozone. A good example of this is this right here, carbon. So hopefully this better illustrates this. Depending on the structure of the carbon, you can have either graphite or diamond. Both are made up of purely carbon, but obviously they're quite different from each other. This is another example of an allotrope. So oxygen, another allotrope of oxygen, is abundant in the ozone layer as well. Oxygen gas is essential for the creation of ozone gas. The ozone layer forms naturally in the stratosphere where ozone and oxygen gas are always converting into each other. And that's, again, as that showed, where UV light will cause the oxygen molecule to break down into atomic oxygen. Atomic oxygen adds on to the oxygen molecule, creates ozone. Breaks apart after, they've hung out for a little bit and they've absorbed some UV light. And then you have that single oxygen atom break off again, find another oxygen molecule, and the process continues. And this is going to show it in this little animatronic image here for you. High in the atmosphere, some oxygen molecules absorbed energy from the sun's ultraviolet rays and split to form single oxygen atoms. These atoms combined with remaining oxygen to form ozone molecules, which are very effective at absorbing UV rays. This thin layer of ozone surrounds the Earth. The amount of ozone required to shield Earth from biologically lethal UV radiation wavelengths from 200 to 300 nanometers, and that's going to be your UVC typically, is believed to have been in existence since 600 million years ago. Before that point, life on Earth was on its own. Why did it only come into existence around that point? We needed the oxygen to create the ozone layer. Basically, the evolution of phytoplankton and plants in general was needed before appreciable levels of oxygen could develop in our atmosphere that allowed for ozone to form in the first place. So, at the time that we're talking about way back in the past, before we had the ozone layer, in fact, oxygen level is approximately 10% of its present atmospheric concentration. And when I say 10%, I don't mean 10% of the atmosphere was oxygen. I mean 10% of what we currently have. Currently, the atmosphere is around 20% oxygen, right? 20%. So the past I'm talking about had 10% of that, or roughly 2% of the atmosphere was oxygen. There was still plenty of oxygen in the ocean, though, so life was completely restricted at this point to ocean life. The evolution that plant life went through to begin the production of oxygen in the atmosphere is what allowed the ozone layer to form and eventually enabled organisms to develop and live on the land. Life on Earth is very complex and tied together. Plants were essentially the pioneers of the land that allowed for us to come after. Just as a food for thought, can you think of any other examples where the evolution or existence of one species or life form allows for the growth or evolution of another? So, ozone played a significant role, as we can tell now, in the evolution of life on Earth and allows life as we presently know it to exist. Ozone is produced naturally in the stratosphere when highly energetic solar radiation strikes molecules of oxygen, O2, and causes the two oxygen atoms to split apart in a process called photolysis. It is a constant interchange of ozone molecules, and oxygen atoms. So ozone is produced by different natural processes in the stratosphere, where it is beneficial, and near the Earth's surface in the troposphere, where it is man-made and harmful. Scientists have established records spanning several decades that detail normal ozone layers during natural cycles. Ozone concentrations in the atmosphere vary naturally with sunspots, seasons, and latitudes. These processes are well understood and predictable. Each natural reduction in ozone layers has been followed by a recovery. Beginning in the 1970s, however, scientific evidence showed that the ozone shield was being depleted well beyond natural processes. It's a very common problem. A chemical or creature or whatever is beneficial where it naturally occurs. So ozone in the natural stratosphere is beneficial. But if it's in a different location, such as in the troposphere where it's man-made and harmful, it can be very dangerous. Can you think of other examples of that kind of situation? Bacteria and diseases are actually a pretty common example, just off the top of my head. If you think of some of our gut intestinal bacteria, just as an example, E. coli. You guys have probably heard of E. coli as bacteria that you can get causes food poisoning, right? It's very commonly found in our gut. In fact, it's very good in our gut and helps with our digestion. But if you take that same E. coli and you put it in a different part of your body, like your stomach or your airways or something like that, very different reaction, I guess we'll say. So in the early 1970s, American chemists F. Sherwood Rowland and Mario Molina theorized that chlorofluorocarbon compounds, or CFC, combine with solar radiation and can decompose in the stratosphere, releasing atoms of chlorine. chlorine monoxide that are individually able to destroy large numbers of those ozone. I cannot talk. Can destroy large numbers of ozone molecules. Along with Dutch chemist Paul Crutzen, Rowland and Molina were awarded the 1995 Nobel Prize for Chemistry for this work. Their research, first published in the journal Nature in 1974, initiated a federal investigation of the problem in the United States, and the National Academy of Sciences concurred with their findings in 1976. In 1978, CFC-based aerosols were banned in the United States, Norway, Sweden, and Canada. So it goes without say, especially because we're talking about it now, that you've probably heard of the holes in the ozone layer. When the ozone is not there to protect Earth, too many of those dangerous UV rays that I discussed earlier reach Earth. This puts us at more risk for getting sunburn, possibly leading to skin cancer, can burn and dry up plants, and interferes with ocean productivity. I've already gone over the increased risk of sunburns and skin cancer, but what about drying up plants and ocean productivity? Plant life depends largely on their leaves to collect sunlight to perform photosynthesis to convert carbon dioxide into oxygen. This is obviously an important process for us as humans that like to breathe said oxygen, but it's also essential for plants because the act of photosynthesis is how plants maintain their energy and continue living. With increased UV radiation, plant leaves would burn up from the increased exposure, limiting their ability to use photosynthesis. These can cause cascade effects like we also talked again about last week. Plant life could begin dying off due to lack of energy or just being too heavily damaged to go on. Plants die off, what do you think happens to the creatures that need those plants to live? They either die or leave, and that continues upward through the food web. One change can have disastrous effects. In addition, the disruption of photosynthesis and plant metabolism can impact food production, which affects all of us. Global warming is being attributed with the melting of polar ice caps and the rise of sea levels, and is possibly linked to the increase of weather-related natural disasters. So how does it work? When chlorine and bromine atoms come into contact with ozone in the stratosphere, they destroy ozone molecules. One chlorine atom can destroy over 100,000 ozone molecules before it is removed from the stratosphere. Ozone can be destroyed, therefore, more quickly than it is naturally created. In this next video that I'm going to show you here, it'll actually show you how chlorine does this.
In this video, you will learn about the famous hole in the ozone layer and why it has got thinner. We will also look at the action the world has taken to restore it back to health. To find out how stratospheric ozone is made and how it stops harmful UV from reaching the ground, view Part A of this video. In the 1980s, scientists found something alarming happening over Antarctica during October when the sunlight returns to the South Pole after winter. The ozone had almost disappeared over large areas, causing the famous hole. An aircraft which analysed the composition of the air flew due south 15 kilometres above the Earth, in the stratosphere where the ozone is most concentrated. They found that the ozone there suddenly became replaced by chlorine oxide. This led to the realization that the chemicals called CFCs, chlorofluorocarbons, were to blame. These are inert, stable molecules and were once the wonder chemical used as the fluid in fridges and air conditioners, to expand polystyrene, and in aerosol cans to propel hairspray and paint and so on. They were completely harmless to animals. So what went wrong? Well, CFCs are so inert that they do not get washed out in the rain or broken down in the troposphere, so they diffuse up into the stratosphere. Use your knowledge about how ozone is formed to think about what might happen to CFCs in the stratosphere. Pause and think. Here they are bombarded with ultraviolet light, which breaks chlorine atoms off the molecule. These then bond with the free oxygen atoms, preventing them from reforming ozone in the ozone-oxygen cycle we saw in the first part of this video. When the chlorine oxide meets yet another oxygen atom, molecular oxygen reforms, leaving the chlorine atom to continue to remove more atomic oxygen. These chlorine atoms are eventually removed from the stratosphere naturally. but not before they have captured thousands of ozone-forming oxygen atoms. Thus the ozone-oxygen cycle was being destroyed, and the ozone layer was thinning all over the world. Thus, in 1987, the Montreal Protocol was signed by all nations of the world, banning the production and eventually the use of CFCs. They have been replaced by HFCs, hydrofluorocarbons, a similar molecule which contains hydrogen in place of chlorine, making them a little more reactive and so able to be broken up in the troposphere before they reach the ozone layer. Because the chlorine is slowly and naturally removed from the stratosphere by complex photochemical reactions, and because the ozone layer is naturally reforming all the time by the action of UV on oxygen, we expect the ozone to return to its original level in 50 or 100 years' time. The hole in the ozone layer allows harmful UV radiation to reach ground level, which can cause skin cancer. However, a common misconception is that it lets heat in and causes global warming, and this is not true. Ozone is also generated in the troposphere by a complex series of photochemical reactions on the products from vehicle exhausts. Here, in the troposphere, ozone acts as a greenhouse gas and helps in the formation of photochemical smogs that pollute certain cities worldwide from time to time, for example, Los Angeles in the USA and Beijing in China.
So that was a good example too of showing that smog that I was speaking about earlier that can form in cities based on ozone in the troposphere. So he kind of touched on it a little bit by getting into CFCs, and we did in a slide or two ago. But it was discovered that certain chemicals used primarily in manufacturing were reacting in the stratosphere and were depleting the ozone layer. So here's a quick list of some of them. We've got our CFCs, our HCFCs, methyl bromide, carbon tetrachloride, methyl chloroform, halons as well. These are all considered ODSs, or ozone depleting substances, and those are their uses on the right there as well. So the world started to realize that if ignored the facts, just ignored what was going on, the Earth was going to reduce the amount of ozone to a level that humans could not survive. This brings us back to the UVC rays. Didn't sound so bad, right? Just some bad sunburns and temporary blindness. That could be our new reality whenever we went outside or just looked out a window, even for just a few seconds. We'd have to become like mole people or something to continue society. And I mean, this image kind of does a backwards way of it, but typically red is actually better in this case, because as you can see with the Montreal protocol implemented, the concentrations actually go up. As you can see in this, going back again to the last slide, you can see higher ozone concentrations are the redder color versus the bluer. So this realization that we had to act and we had to do something brought the leaders of the world together to develop a plan for the future. And as you can imagine, that was probably not an easy task to do. Further validation of their work determining that these chemicals were affecting the ozone came in 1985 with the discovery of a hole in the ozone shield over Antarctica. That's what that nice British man was saying in that video we just watched. Before these findings were to appear, representatives from 28 countries met to discuss the issue at the Vienna Convention for the Protection of the Ozone Layer. The meeting called for international cooperation in research involving ozone-depleting chemicals, or ODCs, and empowered the United Nations Environment Program to lay the groundwork for the Montreal Protocol. So, as anyone can imagine, it's very difficult to arrange a meeting of the world over any subject. Fortunately, since this was such a large magnitude with a catastrophic outcome potentially, if it was not addressed, they kind of had to, you know? So the Montreal Protocol on substances that deplete the ozone layer is an international treaty designed to protect the ozone layer by phasing out the production of numerous substances that are responsible for ozone depletion. It was agreed upon on August 26th of 1987. It entered into force on August 26th, 1989, so literally 2 years later, and then followed by a first meeting in Helsinki in May of 1989. Since then, there's been several revisions, as you can see in that list, just to my left there. As a result of the international agreement, the ozone hole in Antarctica is slowly recovering. Climate projections indicate that the ozone layer will return to 1980 levels between 2050 and 2070. This is also kind of, even though this is like a feel-good story where we are doing the right thing and the ozone is replenishing, it's showing how even temporary advancements that weren't implemented for a very long time, if you think about it, can have impacts that take like a century to recover from. Due to its widespread adoption and implementation, it has been hailed as an example of exceptional international cooperation, with Kofi Annan quoted as saying that perhaps the single most successful international agreement to date has been the Montreal Protocol. Kofi Annan was, I believe, the Assistant Secretary General of the UN at the time. The Montreal Protocol was deemed to be a great success, but global regulation based on the Kyoto Protocol has failed to do so at this point. The many treaties leading up to the present-day agreement have also been remarkable in the overall policy-making process at the global scale, where only 14 years lapsed between a basic scientific research discovery and the international agreement signed in the Vienna Convention in 1985, as well as the Montreal Protocol of 1987. The agreements were structured around several groups of halogenated hydrocarbons that deplete stratospheric ozone, such as CFCs. All of the ozone-depleting substances controlled by the Montreal Protocol contain either chlorine or bromine. Substances that actually contain fluorine do not harm the ozone layer. It's this chlorine and these bromine atoms that break off from their parent structure, if you will, and cause the ozone to be interrupted. Some ozone-depleting substances are not yet controlled by the Montreal Protocol, including nitrous oxide, or N2O. For each group of ODSs, the treaty provides a timetable in which the production of those substances must be reduced and eventually eliminated. There are a couple quotes here. Quotes from the Montreal Treaty were based on the following statement. Recognizing that worldwide emissions of certain substances can significantly deplete and otherwise modify the ozone layer in a manner that is likely to result in adverse effects on human health and the environment, determined to protect the ozone layer by taking precautionary measures to control equitably total global emissions of substances that deplete it, with the ultimate objective of their elimination on the basis of developments in scientific knowledge. The agreement, as I said, laid out the time frame and details of which these ODCs were to be reduced or eliminated, but there were a few that could not be enforced at the time. So why not? A couple of them were deemed essential uses, where there was no acceptable substitute initially found. So there's a couple examples here. In the past, metered dose inhalers, commonly used to treat asthma and chronic obstructive pulmonary disease, these were obviously exempt until we found an acceptable substitute. Also, there was halon fire suppression systems used in submarines and aircraft. Along with agreeing to participate in the reduction and final elimination ODCs, in 1990, a Technology and Economic Assessment Panel was also established as the Technology and Economics Advisory Body to the Montreal Protocol parties. The TEAP, or Technology Economic Assessment Panel, provides, at the request of parties, technical information related to the alternative technologies that have been investigated and employed to make it possible to virtually eliminate use of ozone-depleting substances. The initial agreement was designed to reduce the production and consumption of several types of CFCs and halons to 80% of 1986 levels by 1994, and then to 50% of 1986 levels by 1999. The protocol went into effect on January 1st, 1989. Since then, the agreement has been amended several times to further reduce and completely phase out CFCs and halons, as well as the manufacture and use of carbon tetrachloride, trichloroethane, hydrofluorocarbons, hydrochlorofluorocarbons, hydrobromofluorocarbons, just a bunch of mouthful words. Several subsequent meetings of the signing countries were convened to track overall progress towards this goal and to authorize new changes to the process of phasing out ODCs if they were deemed necessary. So it's important to note that ODC phase-out schedules differ between developed and developing countries. This makes sense, right? Developed countries will have more resources and better ways to actually implement these changes to phase stuff out versus developing countries. The period for developing countries to come into compliance is slightly longer, owing to the fact they have fewer technical and financial resources to introduce these substitutes. In developed countries, the production and consumption of halons formally ended by 1994. Several other chemicals, such as CFCs, HBFCs, and others, were phased out by 1996. For the HRAC technician, this means all R22 refrigerants will stop being produced in the United States by January 1st, 2020. That was 2 years ago now. As per the U.S. Environmental Protection Agency, R22 refrigerant will become illegal in the United States on January 1st, 2020. After that, it can no longer be manufactured and it cannot be imported. But that doesn't mean that it's not around still, as I'll explain shortly. So Canada has guaranteed phase-out level of HCFCs through the ozone depleting substances regulations under the Canadian Environmental Protection Act, imposing the Montreal Protocol reduction schedule on each person engaged in these activities. Relative to the current baseline, you can see how we want to reduce R22 refrigerant throughout the years. So by 2004, we reduced it by 35, by 2010, 65, 2015, 90, and by 2020, we had it reduced by 99.5%, with the goal of complete 100% elimination, that final 0.5% squeaking in at 2030. So, effective of 2015, the manufacturing, using, and selling and importing of all HCFCs are prohibited except for the export or for use as refrigerants until 2020, and HCFC 123, another one, until 2030. Effective January 1st, 2020, the import and manufacture of products containing any HCFC are prohibited, and some activities will be restricted to used, recovered, recycled, or reclaimed HCFCs, but only under a permit. HCFC 123 is used as a refrigerant and for the manufacture of a fire suppression agent used in handheld extinguishers. It's used in air chillers and industrial process refrigeration. When appliances are retired or replaced, it is important that this HCFC 123 is recovered. Leak rates are low for these appliances that use them, and since it can no longer be imported, it can be reclaimed and used in fire suppression and refrigeration and AC equipment that was manufactured before January 1st, 2020. In general, if you own an R22 air conditioner or you're servicing one, you have 3 real choices with them. Just do nothing until the system breaks down. If it does, you can retrofit or convert the old R22 equipment to use an existing refrigerant, or you can replace your system with one containing R410A. There are non-ozone depleting alternatives available if new or retrofitted systems are your choice. Newer alternatives include HFO 1234ZE, as well as R513A, and then of course R410A. R410A may transition to something more environmentally friendly one day. All of those names themselves I just kind of spit out at you. They probably mean little, so I'll explain each of them very briefly. These are not all the possible alternatives. It's simply a small selection of some of them. If I was to go over all of them, we'd be here for hours and hours and hours. I'm going to turn on the light. It's starting to get a little dark. Ooh, nice and bright. So HFO 1234ZE, this chemical actually has a 0 ozone depletion potential and very low global warming potential, which sounds good, right? In open atmosphere, it may actually form HFC 23 though as one of its secondary breakdown products, so something it breaks down into. Unfortunately, HFC 23 is a very potent greenhouse gas, so using this guy is probably not completely advised either. I promise, though, I know you probably see the chemical structure just to my left here. You get a little worried. I promise this won't turn into a chemistry lesson. We have R513A or R513A. Can be used in retrofits or new installations. It's a blend of HFC and HFO refrigerants, and it's also got 0 ozone depletion potential and low global warming potential, so it's a pretty good alternative. And then finally, of the ones we're going to discuss quickly, we have the R410A. It replaced R22 as the preferred refrigerant in residential and commercial air conditioners. It cannot be used in R22 service equipment, though, since it operates at higher operating pressures. So the future does sound pretty good for R410A. It's the primary refrigerant for our residential and commercial units now, and all the older R22 units will eventually disappear as time wears on and the price of the refrigerant increases. So what about the future for R410A? In September of 2014, the United States federal government announced that they were working on voluntary measures to phase out R134A automobile refrigerant across the country. Government is pushing this not because of ozone depletion, which this R134A does not contribute to, but because HFCs contribute to global warming. So kind of a separate issue, but still environmentally worrisome. The measures are voluntary at this point, but they have set their sights on R134A, with the most common replacement for it being HFO1234YF. The YF1 is a near drop in replacement for the R134A refrigerant, but with a global warming potential of just 4, a figure 99.7% lower than R134A. Moreover, the YF counterpart has an atmospheric lifetime of only 11 days compared to 13 years for R134A. For comparison, R12, the one we were talking about a little while ago, has a life of 100 years. That's how long it sticks around. So R134A is an HFC refrigerant, and R410A is also an HFC refrigerant. At this point in time, if nothing else changes, R134A will have another 10 years roughly of mainstream use before it is forced out by government regulation or mandates. If R410A is a close relative to R134A, what will happen to R410A? This is kind of speculation at this point, but it would not be surprising to see the next target is R410A after they're done with R134A. After all, it's the same cycle all over again. In the 1990s, they went after the automotive refrigerant R12 first. Then 20 years later, they went after the residential commercial R22 refrigerant next. So kind of an example of history repeating itself. So in contrast, developing countries phased out CFCs. The list there, you got your carbon tetrachloride, methyl chloroform, and halons by 2010. They're scheduled to phase out methyl bromide by 2015 and to eliminate HCFCs by 2040, which is great. So long term, what are we looking at here? The Antarctic ozone hole grew in size throughout the 1990s and the first decade of the 21st century. The ozone layer over the Arctic also thinned, although not as pronouncedly as over the Antarctic. Despite these findings, most scientists contend that the ozone layer will eventually recover. A reason for this is, as the video we watched earlier demonstrated, the ozone layer is naturally self-replenishing. As those chlorine and bromine and other ozone-depleting substances slowly wither away from the stratosphere, ozone will start replenishing itself and will eventually come back to the concentrations that it used to be, as long as we stick to our guns and continue to do what we can to help let it replenish itself. They note, these scientists, that the success of the treaty is exclusively responsible for the substantial decrease of ODCs, ozone-depleting chemicals, available for release into the atmosphere. Signs of recovery might not become apparent until about 2020, so 2 years ago, however, because of natural variability. According to the World Meteorological Organization and the UNEP, the full recovery of the ozone layer is not expected until at least 2050 over middle latitudes and 2070 over Antarctica. So the Montreal Protocol is also the only universal UN agreement signed by 196 states and the EU. It has more signatories than any other international agreement or body, including the United Nations itself. The protocol was negotiated almost 30 years ago in 1987. It requires its signatories to phase out the use of chlorofluorocarbons, the CFCs, which were the key driver of ozone depletion. CFCs were widely used in aerosol products, firefighting equipment, foams, refrigerators, air conditioning systems, until it was understood how harmful they were to the ozone layer, which provides the Earth with the essential protection from the sun we need in order to just be able to go outside and take a walk. The new addition to the Montreal Protocol, agreed earlier this month, has taken on its next big challenge now that CFCs have virtually disappeared from products. 98% of all ozone-depleting substances have been phased out at this point. Chlorine and carbon are both offending substances in chlorofluorocarbons. Chlorine depletes ozone, but given their carbon content, CFCs are also a greenhouse gas. Despite its focus on ozone, therefore, the protocol clearly has climate change implications. But precisely because of that focus, the protocol had the incidental effect of increasing the use of hydrofluorocarbons as substitutes. HFCs have become the fastest growing source of greenhouse gas emissions, increasing at between 10 to 15% annually. CFCs and HFCs are extraordinarily potent greenhouse gases, thousands of times more damaging than carbon dioxide. So something urgent is needed to be done about HFCs now. This is the idea. We solved one problem, and now we have another problem. And that is what the Montreal Protocol has just achieved, an agreed phase-out of HFCs starting in 2019. The technology for alternatives to fluorocarbons is available, but substitution will take time, especially in lower-income economies. In effect, the Montreal Protocol has morphed into a pure climate change agreement, parallel to the new framework agreement on climate change agreed in Paris in December last year. It was a good decision to keep HFC elimination as part of the Montreal Protocol with its legally binding reduction obligations. The Paris Agreement, which everybody's probably familiar with by contrast, was only made possible by leaving greenhouse gas emissions targets to nationally determined contributions. So why has the Montreal Protocol been so successful compared to other efforts at international cooperation? The agreement not only binds countries, it contains financial provisions to assist in phase-outs. It actually helps as opposed to just dictating things. Now we got this nice little video, this last one. I'll get rid of myself for this guy.
Let me share with you one of the greatest success stories of environment negotiations ever. Indeed, it may be one of the greatest success stories of any sort of negotiations on this planet.
In our long history, there is one unprecedented act of humanity in which every country on Earth came together to protect the future of life on Earth. The Montreal Protocol.
The story of the Montreal Protocol is in some ways also the story of the 20th century. Something that was a great invention, namely a chemical chlorofluorocarbon, had unintended consequences that suddenly became a planetary problem.
It all began with a good idea. In the 1920s, coolants in refrigerators were so toxic that a leak could kill you. So we invented safer chemicals to do the job, CFCs.
The wonder chemicals of the 20th century.
They were so versatile, people's lives were transformed. But in 1974, Sherwood Rowland and Mario Molina predicted that the Earth's natural sun shield, the ozone layer, was being eaten by CFCs at a terrifying rate.
We felt a great responsibility to actually warn society that something could happen.
All eyes turned to the ozone layer. And sure enough, there was an enormous hole in the stratosphere.
It was such a shocking revelation. Over half the ozone layer destroyed above Antarctica in a decade.
If the destruction wasn't stopped, we'd be at risk from lethal levels of UV radiation.
We'd be in dead trouble. We'll have a blind, burnt population.
Faced with this global threat, the world came together to take action. And in 1987, more than 30 countries agreed to phase out the production of CFCs and signed the Montreal Protocol. Over the 3 decades since, the rest of the world's nations have signed up. Together, they've taken on the greatest planetary repair job ever attempted.
It's absolutely terrifying to work on a project that's so important because you know that failure is not an option.
Making the Montreal Protocol a success has taken brilliant minds.
We are working to protect human life.
It has taken determination.
It has made more progress than any other environmental convention in the world.
If the countries of the world engaged in similar deliberations for every issue that faces our world, I would be very happy.
And it has taken ingenuity from an extraordinary global community.
We always have our disagreements, and at the end of the day, we have our agreement.
And it has worked. With CFC's band, the ozone hole is healing. Now it's time to take action again.
You need passion, you need leadership to change the Montreal Protocol into an even better treaty. Victory is within our grasp.
There's only one Earth. We have only one Earth to protect. We cannot lose this one.
Once more, we must come together to protect the future of our planet.
To you, the delegates, and as somebody who considers himself part of the Montreal Protocol family, as you meet in Kigali, look to history, remember where the Montreal Protocol started off from, and please help the world to take the next step. There is need for everybody to compromise, but sometimes out of small steps towards one another, big things can happen, and you, as a family of the Montreal Protocol, have demonstrated that time and time again.
You know, I could watch David Attenborough talk about anything, I think. It's important, too, that the way that our way of thinking should change, too. I've had it in my head for a long time. I forget who it was that told me about this, that for a long time, we as humans, we were basically along for the ride on planet Earth, right? We were evolving, we were growing, we were, developing technology, building cities, expanding into different continents. But we've gotten to the point now where we have enough, not that we have enough technology, we never have enough, we can always keep growing, but we know enough that we can no longer just be a blind passenger on Earth. We're the caretakers of this planet. We're not just simply along for the ride, as it were. We have to do our part and do our best to protect what we have. Otherwise, what's the point, right? There's another saying where, how does it go? Society can only really truly grow when the old are planting trees for the young, knowing that they'll never stand in its shade. Something along those lines. We need to enact things, and we need to perform things knowing that we ourselves personally might not benefit from them, but our children and our children's children, they'll benefit from it. We all stand on the shoulders of giants, right? Our parents, our grandparents, if you want to go even further back, great-grandparents, the great inventors, Einstein, Leonardo da Vinci, they all, furthered the cause, not necessarily knowing if they would even see the fruition of a lot of their technologies or a lot of their thoughts and ideas. We got to continue that. So anyway, sorry, back to the topic here. Controversially, the Montreal Protocol, at least in the early days, also contemplated trade sanctions against non-signatories, although the latter were always given incentives to join. So basically like a slap on the wrist if you didn't join. With the membership at today's level, the use of such measures has become an unnecessary option just because almost everybody's there. The idea of using trade policy as a punishment mechanism in broader climate change discussion has been highly controversial and vigorously opposed. The world more aware of past environmental man-made issues, the move for global agreement became easier yet constantly changing, moving forward to the future. Perhaps it was a specific goal of its focus which made the Montreal Protocol better able to establish strong enforcement provisions as well as strong commitments. There was a readily definable cause and effect relationship. In spite of strenuous opposition from industry in the early days, who challenged the validity of the science, public opinion was supportive of the agreement. I mean, the public wanted the ozone to be protected, so this was an easy win. Solutions were also readily available from both technological and commercial perspectives. In all these ways, circumstances were perfectly aligned for joint action, basically meaning that there was no reason not to. The public was on board, but on top of that, we had alternatives that would actually work for reducing CFCs and other ODC substances. We could immediately just start transitioning, knowing what we would transition to, as opposed to being like, we have this chemical that's dangerous and we need to not use it, but we have no idea what we're going to use instead. Today, there is an organization website with scheduled meetings well into 2020 and beyond set in place to continue the evolving agreement. You can click on the link that's provided if you want to take a quick look at that as well. There are constant changes to update which harmful products are to be targeted, along with attention to the countries that do not conform to the changes. So a little bit of like a little bit of a list of the naughty list, I guess we'll call it. The United Nations continues to be at the forefront, leading the global treaty and implementing the updated changes. Today, the agreement has evolved from a priority to eliminate all CFC products to a more greenhouse gas reduction and elimination basis. Our planet's ability to sustain our lifestyles has brought to light the human ecological footprint we impact upon it. We're just going to touch on this as well, the Paris Agreement. So the Paris Agreement was finalized at a global climate conference in December 12, 2015, and it entered into force in November 2016 after enough countries, including China and the United States, ratified it. The nearly 200 parties to the deal, however, only Syria and Nicaragua failed to sign on. The agreement was committed to voluntary reductions in carbon emissions with the goal of keeping global temperature increases below 2 degrees Celsius, a level that the assembled nations warned could lead to an urgent and potentially irreversible threat to human societies and the planet. This increased temperature would have disastrous effects on our polar ice caps, as well as rising sea levels, and then it would just it would change the landscape entirely by changing biomes entirely. We'll be speaking about that in a future week, so I won't go too much into it, at least right now. So under the New Deal, countries will evaluate progress towards their goals in 2018, and beginning in 2020, they submit updated carbon reduction plans every 5 years. So the next one will be in 2025. The details on how countries' efforts will be monitored, verified, and reported are subject to negotiations that are constantly ongoing, but as are the specifics of a proposed $100 billion in climate-related financing meant to help poorer countries adapt to these changes that are being implemented. And then we had June 1st, 2017, where Donald Trump announced that the United States would become the only country to withdraw from the Paris Agreement. He was a strong criticizer of the Paris Agreement back when he was running for president, and then including when he became president, up until the point where in 2017 he announced that the United States would exit the agreement. He was claiming that it would that the cutback on carbon emissions would kill jobs and impose onerous regulations on the U.S. economy. With the United States producing nearly 1/5 of all global emissions, withdrawing from the accord could undercut collective efforts to reduce carbon output, transitioning to renewable energy sources, and just lock in the future climate measures and changes that are already underway. And then, if anybody's getting whiplash, in 2021, Joe Biden became president, and he entered the United States back into the Paris Agreement. So, to finalize the last couple things about the Montreal Protocol, Kofi Annan, as I indicated when we heard his name last, a bunch of slides ago, was the Assistant Secretary General of the United Nations at the time when the Montreal Protocol came to be. His report on sustaining our future deals with environmental issues. So although he celebrated the success of the Montreal Protocol, in the very next breath he wrote, "Nevertheless, we must face up to an inescapable reality. The challenges of sustainability simply overwhelm the adequacy of our responses, with some honorable exceptions, and our responses are too few, too little, and too late." He's basically stating, and this is something that I'm sure many people can agree with, is that humans on the whole are very reactionary. We wait, not necessarily until it's too late, but we get close sometimes to the buzzer before we enact changes necessary to prevent or protect or just to prevent stuff. The ozone layer is probably a good example of where we didn't do that almost, because we just got into action as soon as we found out about it. But countries still dragging their heels, and the United States, as an example of the Paris Agreement, is a good example of countries just kind of waiting and dragging their heels on getting stuff involved to prevent climate change. Kofi Annan also said only governments can create and enforce environmental regulations and devise more environmentally friendly incentives for markets to respond to. To cite but one example, governments can make markets work for the environment by cutting the hundreds of billions of dollars to subsidize environmentally harmful activities each and every year. Another is by making greater use of green taxes based on the polluter pays principle. And that brings us to the end of this week's lecture. Next week, I'll kind of take my face off here so you can read the whole thing. But next week, we'll be talking about the ecological footprint. So we'll be going over that information. And I also want to have a quick reminder that the assignment for the carbon footprint, assignment number 1, you can find it in the assignments folder up on Blackboard. It will be due February 4th at midnight. I hope everybody enjoyed the presentation, and I hope to talk to you guys soon. Until then, have a great weekend, have a great week, and we'll be talking again soon.